Hello dear students, welcome to Wallah. So I hope you are doing well. Now this is a one short series and today we will discuss about the internal force of convection, right? And in previous session we discussed about the external force convection, and today's session is completely on internal force of convection, right? So what topics we will cover in this session? So first we will discuss about the basics of internal flow. What is the internal flow, right? So any flow inside the closed conduit, that is known as the internal flow. The flow may be inside the pipe, right, or inside the tube or inside the duct, right? So that is the internal flow. Basically that flow inside the closed conduit, that is the internal flow, right? After that we will discuss about the concept of average velocity. What is the average velocity, or you can say mean velocity, right? And after that we will discuss about the bulk mean temperature, or simply you can say mean temperature, right? Or it is a mixing cup temperature also. It is also known as the mixing cup temperature. And after that we will discuss about the empirical expression for the Nusselt number, right? So before discussing about the internal force convection, right, first we will discuss about the internal flow, right? Internal flow. So what is the internal flow? Internal flow. So as I already told, internal flow, the flow inside the closed conduit. Flow inside the closed conduit. Right? Closed conduit. The closed conduit may be pipe. Say this is a pipe. Okay, this is a pipe. So flow inside the pipe. Right? Duct. So this is the duct. So this is the duct. So flow inside the duct. So this is also example of the internal flow. Or see here. Now see, if flow occurs this annular space, this is also the internal flow. So these are the some example of the internal flow. Okay. Now see, to understand the internal flow concepts, I am considering the pipe flow. So let us assume there is a pipe. And this is the center line of the pipe, right? And this radius is capital R. Radius of the pipe is capital R. This is the radial direction. R is equal to 0. R is equal to 0 at the center line. Okay. And flow occurs inside this pipe. So whenever the real fluid come into contact with the solid surface, then there is a formation of the boundary layer. So this is the 2D plane, And in 2D plane, this is the 2D plane now, and in 2D plane the boundary layer formed like this, see. Right, see, after some distance that boundary layer merges, after some distance boundary layer merges. So this distance, see here, this distance here to here, this distance or this region is known as developing region. This region is known as developing region. This region is known as the developing region, and the length is known as the entrance length. This length is known as the entrance length, XLEH, hydrodynamic entrance length. You can say hydrodynamic entrance length, right? That XLEH, this is the hydrodynamic entrance length. Hydrodynamic entrance length. Hydrodynamic entrance length. Okay, and this is the developing region, and in developing region the velocity profile, if you are observing the velocity profile, that velocity profile changes. So I am considering one section here and another section here, So inside the boundary layer, so this is the inner region, na? Inside the boundary layer, that velocity changes. So here the velocity is 0, right? At the wall the velocity is 0. Here also at the wall velocity is 0. And outside the boundary layer, everywhere the velocity is same. Or I can say every layer having same velocity. Okay? See. So this is the velocity profile. At this section. And if you are observing the velocity profile at this section, so this is the velocity profile at this section. Right. So I am considering this is a section. Let us assume this is a section 1, 1. Let us assume this is the section 1, 1. This is a section 1, 1, and this is a section 2, 2. This is a section 2, 2. So section 1, 1 and the section 2, 2, the velocity profile is not same. The velocity profile is changing. So in the developing region, we can say that velocity profile is not constant. The velocity profile is not same. The velocity profile is changing. Is it clear? So in the developing region, if you are observing here, in the developing region, that velocity is function of r and x both, right? In the developing region, the velocity is function of r and x both, or we can say at a particular r, u is function of x. That means du by dx at a particular r is not equal to 0. That means, see here, if I fix the radial distance, now see, if I fix the r, see here, I fix the r, ठीक है ना? I fix the r. This is the r. This is the r. I fix the r. So see here, at the section 1, 1, this layer having different velocity, this layer having different velocity. So if I fix the r, right, so at a particular r, that velocity is changing with respect to x. In which region? In the developing region. So what is the meaning of the developing region? In the developing region, the velocity profile is continuously changing with x, right? Continuously changing with x. What is the x direction? See, this is the x direction. No? This is the x direction. This is the x direction and this is the r direction, radial direction. X, r. Okay. So in the x direction, the velocity profile is continuously changing, right? At a particular r, that u is a function of x, that means du by dx at a particular r is not equal to 0. This is the story of developing region. This is the story of developing region. Hydrodynamically developing region, because in future we will discuss about the thermal developing region also, right? So this is the story of the hydrodynamic developing region. Now come to the developed region. So in the developed region, again I am considering a two sections. So one section is here and another section is here, right? Now see here in the developed region. So this is the developed region, right? This is the developing region and this is the developed region. This is the developed region. This is the developed region, right? And in the developed region, if you observe the velocity profile, right? This is the velocity profile. This is the velocity profile. And if you see the velocity profile at this section, so again here the velocity is 0. Just 1 minute. I extend this pipe up to here. Okay. Okay. See here. So this is the velocity profile. This is the velocity profile. Right, this is the velocity profile. So that velocity profile is not changing with respect to x. The velocity profile is not changing with respect to x. And if you fix the radial distance, if you fix the radial distance, if I fix the r, so in developed region, what we are observing, in the developed region, what we are observing, right, u is function of x only. Sorry, u is function of r only, sorry. U is function of r only. U is not a function of x. U is a function of r only. So if you fix a particular radial distance, I fix a particular radial distance, so change of velocity, change of u with respect to x at a particular r is equal to 0. What is the meaning of that? Right? If you fix the r and if you are observing the velocity here and if you are observing the velocity here, both the velocities are same. That means we can say that velocity at a particular r, the velocity u is not a function of the x, not a function of the x. Is it clear? So this is the story of the developed region. So in the developed region, the velocity profile is not changing. At a particular r, the u is not a function of x. Whereas in the developing region, profile continuously changing, right? And the at a particular r, u is a function of x. U is a function of x. Is it okay? Right. Now see, what is this entrance length, this hydrodynamic entrance length? So there is some empirical relation. There is some empirical relation for this entrance length. So that entrance length, hydrodynamic entrance length. What is this hydrodynamic entrance length? Right. How I calculate this hydrodynamic entrance length? Right. So first, you know the flow is laminar or turbulent inside this pipe. Right. First, you have to understand what is the condition of the flow. What is the type of the flow? Laminar flow or turbulent flow? Right. So to calculate the to understand the flow is laminar or turbulent, first you calculate the Reynolds number. Right. And on the basis of value of the Reynolds number, we can comment the flow is laminar or turbulent. Right. So first calculate the Reynolds number. So what is the Reynolds number? I already discussed what is the Reynolds number. The Reynolds number is ratio of inertia force to viscous force. Ratio of inertia force to viscous force. What is the inertia force? That inertia force is Fi. What is the viscous force? That viscous force is Fe. So if you derive the mathematical expression for the Reynolds number, so what you are getting? You are getting this rho u L c by mu. Okay? Or u L c by nu. What is the nu? Nu is the kinematic viscosity. What is the mu? Mu is the dynamic viscosity. Rho is the density. U is the velocity. Lc is the characteristic dimension. Now, in case of the internal flow, in case of internal flow, this U is U average, or you can say U mean, right? And what is the U average or U mean? This is the average velocity. This is the average velocity or mean velocity. This is the average velocity or mean velocity, right? Now, what is the LC? What is this LC? This LC is characteristic dimension, and mathematically it is 4 into cross sectional area divided by weighted perimeter, right? So if there is a pipe flow, if I am talking about the pipe flow, so pipe flow occurs like this. The diameter, let us assume that diameter is capital D. So what is the LC? This LC is equal to 4 multiplied by what is the cross sectional area or flow area, pi by 4 d square, divided by weighted perimeter. This is pi d. 4 pi 1 d another d. So LC is equal to d. So in case of the pipe flow, that LC is equal to capital D. Right? And sometimes this LC is also known as the DH, hydraulic diameter, right? If suppose you are dealing with the non-circular cross section, I can say non-circular cross section member, right? Like a duct. Duct is a non-circular. Generally, duct is a non-circular. Duct is circular also, but if you are dealing with the non-circular cross section, right? Non-circular cross section, then find out the DH. What is the DH? This DH is the hydraulic diameter. Right? So LC is equal to DH also. right? Hydraulic diameter. This is the hydraulic diameter. This is the hydraulic diameter. Hydraulic diameter. So see here. These are the some example of the internal flow. No? These are the some example of the internal flow. So this is a pipe flow. If let us assume this is a duct, and this duct having dimension, this is the A and this is the B. So can you tell me what is the LC here? And let us assume such type of passage. So let us assume that inner dia is a small d and the outer dia is capital D. Outer dia is capital D. So can you tell me what is the LC in this case? What is the LC in this case? Can you tell me what is the LC? So in this case, that LC is internal flow, 4 into what is the flow area? That is A into B cross sectional area divided by that is weighted perimeter, that is 2A plus B. So this is 2 2s are 4 and this is equal to 2AB upon A plus B. 2AB upon A plus B, right? 2AB upon A plus B. Now in this case, what is the LC? What is the LC? What is the flow area here? So this is flow 4 into pi by 4 capital D square minus small d square. This is the cross sectional area multiplied by weighted perimeter. So weighted perimeter, this is a pi d plus this is pi d. Okay. So 4 cancel out. Okay. This pi cancel out. Capital D square minus small d square. So capital D minus small d plus capital D plus small d. So ultimately LC is equal to capital D plus small d. So this is the LC. Sorry. Capital D minus small d. Sorry. Capital D minus small d. Sorry. Right. Capital D plus small d. Na? So if you are expanding this A square minus B square, A minus B, A plus B. Right. So capital D plus small d cancel out from the numerator and the denominator. So only that capital D minus small d is remaining. Okay. So this is the LC. So I think LC concept is clear, right? So in case of the internal flow, U is the average velocity. Now see here, if you are calculating the Reynolds number, and if this Reynolds number is less than or equal to the critical Reynolds number, you are calculating the Reynolds number, and the Reynolds number is less than or equal to critical Reynolds number, then flow is laminar flow. Then flow is laminar flow. Right? And if Reynolds number is greater than the critical Reynolds number, then flow is turbulent flow. There is transition of the flow also in a certain range of the Reynolds number value. There is a flow transition also, but we are not dealing with that transition reason. So directly I say if Reynolds number is greater than the critical Reynolds number, so that is a turbulent flow. And in case of the internal flow, what is the critical Reynolds number? The critical Reynolds number is equal to 2000. In some books it is 2300 also, that is also correct, that is not wrong, right? In some standard book you are getting the critical Reynolds number in case of the internal flow 2300 also, that is also correct. Okay, so I am taking 2000. Okay. Now see here, so I already told you that hydrodynamic entrance length depends on the flow is laminar or turbulent. So in case of the laminar flow, if laminar flow is there, so this entrance length, hydrodynamic entrance length, is equal to 0.05 Reynolds number into T, right? This is the experimental value, or you can say this is the experimental obtained mathematical expression. This is the empirical relation, right? And in case of the turbulent flow, this XLEH, hydrodynamic entrance length, this is approximately equal to 10 times of the diameter, right? So in case of the turbulent flow, the dependency of the hydrodynamic entrance length, with Reynolds number is negligible, I can say, right? in case of the turbulent flow, right, that hydrodynamic entrance length is not much dependent on the Reynolds number, whereas in the laminar flow, this hydrodynamic entrance length depends on the Reynolds number, strongly depends on the Reynolds number, right? So in case of the turbulent flow, this hydrodynamic entrance length is approximately, no? This gives the approximate result. But that is okay. There is no issue on that. Right? So in case of the turbulent flow, that hydrodynamic entrance length is not a strong function of the Reynolds number. Whereas in case of the laminar flow, that hydrodynamic entrance length is a strong function of the Reynolds number. So please keep this point in mind. Okay? Now, let's start our discussion on the average velocity. So these are some basics related with the internal flow, right? Now let's start our discussion with average velocity. What is the average velocity? Average velocity, or it is also known as mean velocity. Average velocity or 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 mean velocity. So to understand the average velocity or mean velocity, I am considering two identical pipes. So these are the two identical pipes, and consider this section. Okay, this is a center line. Here also this is a center line. Okay, and radius, here also the radius is capital R, and here also the radius is capital R, right? So we know that at a particular section, velocity, right? And see one thing, we are mainly focused on the developed region, because that developing region is very small. Matlab, if you consider a pipe, a long pipe, let us assume if I consider a pipe of 5 meter length, right? So that length of the entrance length, may be 10 centimeter, maybe it is a 20 centimeter, maybe it is a 5 centimeter. So pipe is 5,000 centimeter, 5 meter, 5,000 centimeter, and this entrance length, this developing region is 5 centimeter or 10 centimeter. So in most of the span of the pipe, the flow is fully developed flow. That's why our focus on the fully developed flow, not the developing flow, because in a pipe, in most of the length, or I can say in a length of the pipe, the flow is fully developed flow. That's why our main focus is on the fully developed flow, not the developing flow. Okay, so here also my focus is on the fully developed flow. So at a particular section, we know that that velocity, see here, at a particular section, this is the velocity profile. U is function of R. Right? Now see here, what is the average velocity or what is the mean velocity? So first I write here the definition, right? Average velocity is a hypothetical velocity. Average velocity is a hypothetical velocity hypothetical velocity that gives the same mass flow rate same mass flow rate as actual velocity profile gives. As actual velocity profile gives. Right, average velocity is a uniform hypothetical velocity, na? Average velocity is uniform hypothetical velocity that gives the same mass flow rate as the actual velocity profile gives, right? So if I considering average velocity profile here, average velocity profile. So this is the distribution of the average velocity profile. This is the average velocity profile. Right? This is the average velocity. This is the average velocity. Okay, this is the average velocity. Right, this is the average velocity profile and this is the actual velocity profile. So if you are calculating the mass flow rate, by considering the actual velocity profile, or I can say if you are calculating the mass flow rate by considering the variation of the velocity, right, variation of the velocity, and if you are calculating the mass flow rate by considering the average velocity. So let us assume this is the m dot dash, this is the m dot dash and this is the m dot, right? So this m dot dash and this is the m dot dash and this is the m dot, right? So see here, what is the definition of the average velocity? The average velocity is a uniform hypothetical velocity that gives the same mass flow rate as the actual velocity profile. Average velocity is a uniform hypothetical velocity that gives the same mass flow rate as actual velocity profile gives. That means m dot dash is equal to m dot. M dot dash is equal to m dot. M dot dash is equal to m dot, right? So if you are calculating this m dot and calculating this m dot dash, so both m dot dash and m dot is same, right? So I'm not performing a derivation here, okay? I'm not performing derivation here. I directly write here, right? What is the average velocity? What is the mathematical expression of the average velocity? What is the mathematical expression of the average velocity? So this average velocity is, this average velocity is 2 by r square, 0 tends to r, u of r dr. This is a mathematical expression of the average velocity. And from where this mathematical expression come? From where this mathematical expression come? This mathematical expression come when you are equating the mass, when you are equating the mass flow rate when you are equating the mass flow rate by considering the variation of the velocity and when you are considering the mass flow rate by when you are calculating the mass flow rate by considering the average velocity. So see here, again I am repeating. You are calculating the mass flow rate by considering the average velocity. You are calculating the mass flow rate by considering the velocity profile or velocity variation. Both the mass flow rate are same. If you are equating both the mass flow rate, then what you are getting this, right? So I am not deriving here, okay? I am directly right. Okay. So this is the average velocity. Okay. Now, This is the average velocity. And see, if I'm talking about the, let us assume if flow is laminar flow. So in case of the laminar flow, from the fluid mechanics concept, we know that in case of the laminar flow, what is the velocity profile? U is a function of r, we know that. But how u is changing with respect to r? How u is changing with respect to r? So this is the parabolic velocity profile. 1 minus small r square by capital R square. Right, this is the velocity variation with r in the fully developed region for the laminar flow. Right, u is equal to u maximum 1 minus small r square by capital R square. And from here, if you are calculating the average velocity, so this average velocity is equal to u maximum divided by 2. And this u maximum is nothing but the center line velocity also. What is the u max? U maximum is u maximum or uc, right? This is maximum velocity or center line velocity. Maximum velocity or center line velocity. Center line velocity, right? At the center line that velocity is maximum, at the center line that velocity is maximum. Okay, so in case of the laminar flow, you are getting this relation. U average is equal to u maximum by 2, or simply you can say u maximum is equal to 2 times of u average. Fine. Now, come to the next concept, which is a concept of bulk mean temperature. Next concept is bulk mean temperature. Next concept is bulk mean temperature. Bulk mean temperature, or simply we can say mixing cup temperature. Mixing cup temperature, bulk mean temperature or mixing cup temperature. Okay, and it is denoted by Tm. So what is a Tm? Now see here. Okay, now see, if I considering a pipe, and let us assume this pipe surface temperature is Ts. Let us assume this pipe surface temperature is Ts. This pipe surface temperature is Ts. Okay, and Ts is, I say, this is the surface temperature. This is the surface temperature. This is the surface temperature. And fluid is flowing inside this pipe. Fluid is flowing inside the pipe. Okay, so here also, right, and let us assume here the fluid temperature, that is T. Fluid temperature is T. That fluid inlet temperature, that is T. And I'm assuming here ki this T is lesser than the Ts. I'm assuming here Ts is greater than Ts. Ts is greater than T, right? So heating of the fluid occurs, na? Heating of the fluid occurs because Ts is greater than T. So I say the heating of the fluid occurs, na? Heating of the fluid occurs, right? So like a hydrodynamic boundary layer, like a hydrodynamic boundary layer. Here the thermal boundary layer come into picture. Right? And up to this length, let us assume up to this length, right? This is thermally developing region. This is the thermally developing region. And this length is XLET. Right? XLET. And what is the XLET? This is the thermal entrance length. XLT. This is the thermal entrance. This is the thermal entrance length. Okay. Now, This region is a thermally developing region. Now this region is thermally developed region. This region is thermally developed region. This region is thermally developed region. Thermally developed region. Okay, fine. Now see here at this particular section, and this is a central line. Na? This is a central line, correct? R is equal to 0 here, and this is the radial direction. Now see here, Ts is greater than T, so at this particular section, if you see the temperature variation, the temperature variation is like this, right? This is a temperature variation. This is the temperature variation. This is the temperature variation at this particular section. At this particular section, this is the temperature variation. Is it okay? Is it okay? And if you see the temperature variation at this particular section, then now first extend this pipe till here. Okay. Now see, at this particular section, again this is a Ts, this is a Ts. So I'm assuming here Ts is not a function of x. No? I'm assuming Ts is constant. Ts is constant. I'm assuming Ts is constant. Ts is not a function of x. So at this particular section, okay, this is the velocity profile. This is the velocity profile. This is the velocity profile. Is it clear? So in the developed, in the thermally developed region, na, in a thermally developed region, the temperature, see here, it is not like a hydrodynamically developed region. It is not like a hydrodynamically developed region. In the thermally developed region, na, in the thermally developed region, T is function of R as well as X. Right? See, in the hydrodynamically developed region, U is the only function of R. U is not a function of X. But in case of the thermally developed region, T is, in case of the thermally developed region, T is function of R and X both. T is a function of R and X both. Is it clear? Is it okay? Is it okay? Tell me guys, is it okay? Is it okay? Okay. And that's why in the thermally developed region, because in thermally developed region, see here, in thermally developed region, this T is a function of R and X both, right? So to define the thermally developed region, I am considering a dimensionless term. Dimensionless term, and that dimensionless term I am considering, that is theta. Dimensionless term, na? Or dimensionless, you can say temperature difference. Dimensionless temperature difference, and that is theta. And what is this theta? This theta is equal to T minus TW upon or T minus TS. because surface temperature is Ts, T minus Ts, and this is Tm minus Ts. Okay. This dimensionless temperature difference, that is theta. So this theta is equal to T minus Ts upon Tm minus Ts, or you can write in this way also, because this T is function of R and X both, minus surface temperature. Here I am assuming surface temperature is constant, but in case of the constant heat flux case, right, there are two cases, na? Like a external force convection. There are two cases. One is a constant wall temperature case, and another one is a constant heat flux case. So in constant wall temperature case, this Ts is fixed, this Ts is constant. But in case of the constant heat flux, this Ts is not constant, Ts is a function of X. Right? That's why, I am taking here T as a function of X to generalize the things, right? Tm, this Tm is a function of X. What is the Tm? Tm is the mean temperature. Tm is the mean temperature, right? And Ts, again this is the surface temperature. So I am defining a dimensionless temperature difference. I am defining a dimensionless temperature difference, that is theta, and this is the theta. So see here, in the thermally developed region, T is a function of R and X. That means we can't write here at a particular, see here, we can't write here at a particular R, the dt by dx is not equal to 0, because at a particular R, the temperature is changing with respect to X. If you fix the R, see here the temperature is different, because that fluid is continuously heated, no? The fluid is continuously heated with X. If I say, let us assume at this particular section, that mean temperature, let us assume at this particular section, at the inlet, that mean temperature is, let us assume, 30 degrees Celsius. Surface temperature, let us assume that is a 150 degrees Celsius, and at the exit of the pipe, the temperature is 90 degrees Celsius. So what happening here? The fluid is continuously heated now from 30 degrees Celsius to 90 degrees Celsius. Is it fine? So at this section and at this section, if you consider a particular layer, so that layer don't have a same temperature, or that layer does not have the same temperature. See here, at a particular R, this layer having a different temperature, and this layer having a different temperature. Right? If you fix R, if you consider a layer at this section, this layer having a different temperature, this layer having a different temperature. Is it fine? That's why we can say T is function of R and X both in the thermally developed region also. Right? So we can't write this in the thermally developed region. That's why we define a term which is a theta. Yes, for the theta we can say this d theta by dx at a particular R, that is equal to 0. For theta we can say, right, for the theta we can say that d theta by dx at a particular R, this is equal to 0. Right? And that is the reason we define a term theta. Is that clear? Right. Okay. Now see here, T we know, Ts we know. What is this Tm? This Tm is the mean temperature. Right? This Tm is the mean temperature. Now let's start our discussion on the mean temperature only. Mean temperature. What is the mean temperature? So see here. At a particular section, this is a particular section. Okay, in a thermally developed region, let us assume this is the temperature profile. At a particular section, temperature is a function of R. Okay, so this is the radial direction. Now I'm considering the average, now I'm considering a mean temperature. At this particular section, I want to calculate the mean temperature. So what is the mean temperature? What is the mean temperature? So this is the mean temperature. This is the mean temperature. Right, so what is the definition of the mean temperature? See here. What is the definition of the mean temperature or bulk mean temperature? Bulk mean temperature or mean temperature. Bulk mean temperature or mean temperature. Bulk mean temperature or mean temperature. See here. Bulk mean temperature, bulk mean temperature, bulk mean temperature is hypothetical temperature that gives the same enthalpy rate as actual temperature profile, gives. Right, what is the bulk mean temperature? The bulk mean temperature is a hypothetical temperature that gives the same enthalpy rate as actual profile gives. Right, so if you are calculating the enthalpy rate here, let us assume this is a H dash. If you are calculating the enthalpy rate by using the temperature variation at this particular section, T is a function of R. Na? At this particular section, if you consider a particular section, then I can say na T is a function of R, right? So in general, T is a function of R and X also, R and X both, right? If you are changing the X, if I am talking about this particular section, right? So T is function of R and X both. But if I fix the X, if I fix the section, then T is a function of R only. And this is a variation of the mean temperature. That is a uniform variation. Okay. So if you are calculating the enthalpy rate by considering the temperature profile, and if you are calculating the enthalpy rate, by considering the mean temperature, okay, so this H dot, this is the enthalpy rate here, and this is the enthalpy rate by considering the mean velocity or bulk mean, mean temperature or bulk mean temperature. Okay, so this profile gives the enthalpy rate. If you consider the variation of temperature, with R, if you are calculating the enthalpy rate, you are getting this enthalpy rate H dot. If you consider the mean temperature, then you are getting enthalpy rate H dot dash, and both the enthalpy rate will be same. So if you are equating both these two, what you are getting this, that mean temperature is equal to, 0 tends to R, T of R, U of R, R dr. T is a function of R, U is a function of R, 2, 0 tends to R, U of R, R dr. Right, this is the mathematical expression for the mean temperature. So at any particular section, if you want to calculate the mean temperature, if you want to calculate the bulk mean temperature, you know the temperature variation at that particular section, and you know the velocity variation at that particular section. Then you are able to find out the mean temperature at that particular section. Is it fine? If I want to calculate the mean temperature at this particular section, so I know how the velocity varies with R at this particular section and how the temperature varies with R at this particular section, then I'm able to find out the mean temperature. Then I'm able to find out the mean temperature. Okay, so this is the mathematical expression of the mean temperature. That is very, very important. This is very, very important mathematical expression. Is it clear? Now, come to the next very, very important part, or very, very important observation. What is that observation? See here. The variation of Nusselt number, and the convective heat transfer coefficient. So again, see, in a pipe there are two regions now. One is a developing region. So this is the developing region and this is the developed region. This is the developing region. This is the developing region and this is the developed region. Developing region and the developed region, right? In the y axis Nusselt number, or this is the convective heat transfer coefficient. Now this is the x direction. Okay, this is the axial direction. Now see, if you see the Nusselt number variation and the convective heat transfer variation it is like this. This is the variation, right? In the developing region, that Nusselt number and the convective heat transfer coefficient decreases, and it decreases, and at the developed region it is almost constant. This is the variation of the Nusselt number and the convective heat transfer coefficient, because by using the Nusselt number you are calculating the H, right? In this case, what is the Nusselt number? How that Nusselt number, in case of the internal flow, this Nusselt number is equal to H dH by Kf. H dH by Kf, right? That HLC by Kf, that Nusselt number is HLC by Kf. So in case of the internal flow, what is the mathematical expression of the Nusselt number? H, convective heat transfer coefficient, dH. This dH is hydraulic diameter. If this is the pipe flow, if pipe flow is there, then dH is equal to d. So dH is hydraulic diameter. I already discussed hydraulic diameter. dH is the hydraulic diameter. Kf is the thermal conductivity of the fluid. Kf is the thermal conductivity of the fluid. Is it okay? Okay. Now here. No. Okay. So this is about the Nusselt number. Now come to the empirical relations. Now, in case of the internal force convection, in case of internal forced convection, there are two cases. In case of the internal force convection, the flow may be laminar flow. The flow may be turbulent flow. The flow may be laminar flow. The flow may be turbulent flow. The flow may be laminar flow. The flow may be turbulent flow. So if the flow is laminar, so in case of the laminar flow, there are two cases. One is the constant wall temperature case. Ts is constant wall temperature case. And another one is a constant heat flux case, which is Q dot. Q dot is equal to constant, like a external force convection, right? In case of the laminar flow, there are two cases. One is the constant wall temperature case. That means Ts is not a function of x. And second one is the constant heat flux case. That means Q dot is not a function of x, right? Now see, if constant wall temperature case is there, so in this case Nusselt number is equal to 3.66, right? I am talking about the fully developed region. Again I am repeating, I am talking about the fully developed region, thermally fully developed region, right? That's why Nusselt number value is constant. In the thermally fully developed region, the Nusselt number value is constant, and that's why here you are not observing x term is here. You are observing x term is not here. X term is not here. You are observing that X term is not here. That is constant. I am talking about the thermally fully developed region. Okay? So Nusselt number is 3.66, and in case of the constant wall temperature, constant heat flux case, that Nusselt number is 4.364. 4.364. Right? Whereas in case of the turbulent flow, we are using the Dittus. Generally, we are using this Dittus-Boelter equation. This Dittus-Boelter equation, and as per the Dittus-Boelter equation, Nusselt number is equal to 0.023, Reynolds number to the power 0.8, and Prandtl number to the power 0. Prandtl number to the power, that is n. Prandtl number to the power n. Prandtl number to the power n. Right. Now see here. Just 1 minute. Okay. Now n. This n, right, n is equal to 0.4 if heating of the fluid occurs. If heating of fluid occurs. What is the meaning of that? Right? Wall temperature, surface temperature is more as compared to, surface temperature is more as compared to the fluid temperature. So definitely heating of the fluid occurs. If n is equal, if cooling of the fluid occurs, then n is equal to 0.3. Right? Cooling. Right? Cooling of the fluid occurs. If cooling of the fluid occurs, then n is equal to 0.3, and if heating of the fluid occurs, then n is equal to 0.4. Is it clear? So remember this empirical relation. And one thing that I forget it, see here, about the hydrodynamic entrance length, thermal entrance length. Where is the thermal entrance length? Okay. Where is the thermal entrance length? This is the thermal entrance length. This is the thermal entrance length. So, see. Okay. Now thermal entrance length, see here. Again that thermal entrance length, mathematical expression of the thermal entrance length, that depends on the flow is laminar flow, your flow is turbulent flow. Flow is laminar flow or flow is turbulent. Now see, XLET, thermally entrance length, this is equal to, for the laminar flow, this is 0.05 Reynolds number D, and Reynolds number into D into Prandtl number. Whereas in case of turbulent flow, that thermal entrance length, this is approximately equal to 10 times of the dia. So if you want to establish the relation between the hydrodynamic entrance length and the thermal entrance length, so it is very much clear this term is equal to XLEH, this is equal to hydrodynamic entrance length, right? So I can say that thermal entrance length is equal to hydrodynamic entrance length multiplied by Prandtl number, or I can say, see here, this relation is very, very important. No? Thermal entrance length to hydrodynamic entrance length, this is equal to Prandtl number. This is equal to Prandtl. This ratio is equal to Prandtl number. And here, that thermal entrance length is equal to the hydrodynamic. In case of the turbulent flow, there is no problem. In case of the turbulent flow, right, the thermal entrance length is equal to the hydrodynamic entrance length. But in case of the laminar flow, that ratio, this ratio is depends on the Prandtl number. If Prandtl number is equal to 1, then both the entrance length is same. If greater than 1, less than 1, then you can easily comment on that. Okay. Now, okay. Now come to the, in laminar flow there are two cases, no? constant wall temperature case and constant heat flux case. So first focus on the constant wall temperature case. Now constant wall temperature case. Constant wall temperature case. See here. Constant wall temperature case. In constant wall temperature case, that means Ts is constant, not a function of x, not a function of x. Okay, and if I considering a pipe here, this is the pipe, this is the pipe, this is the inlet of the pipe, this is the exit of the pipe, and at the inlet of the pipe, the mean temperature is TMI. What is that? What is the TMI? The TMI is the mean temperature at the inlet. What is the TME? This is the mean temperature at the exit. And what is the TS? The TS is the surface temperature. TS is the surface temperature. Okay, so TMI TMI is the mean temperature at the inlet. TME is the mean temperature at the exit. Ts is the surface temperature. Since we are discussing about the constant wall temperature case, that's why Ts is not a function of x. Ts is constant, right? Now see, this mean temperature is a function of x. See here, this is the x direction, this is the x direction, and this is the flow direction. This is the flow direction. I'm assuming Ts is greater than TMI. I'm considering Ts is greater than TMI. If Ts is greater than TMI, then heating of the fluid occurs now, right? Let us consider some numerical values, then it is easy to understand. Let us assume Ts is 150 degrees Celsius. TMI, let us assume this is 30 degrees Celsius. And TME, let us assume this is 100 degrees Celsius. Now see here, what happened? What happened? See here, what happened? Right, as we are moving in the x direction, the mean temperature changes with x, na? Mean temperature changes with x, na? Mean temperature changes with x, yes or no? The mean temperature is a function of x, yes or no? Yes, sir. Mean temperature is a function of x. Mean temperature is a function of x. Is it fine? Now my question is that how this mean temperature changes? How this mean temperature changes? This is my question. Right. If I want to calculate at this particular section mean temperature, so let us assume this is TMX. What is the TMX? Right. So first question is how the mean temperature is changing with respect to x. That is the first question. And second question is that if I want to calculate the mean temperature at any particular x, then how I calculate? Is it fine? Is it clear? Okay. Now see here. Again, I'm not deriving here. Whatever the important mathematical expression, I directly write those mathematical expression here. Right. So I'm not deriving it. So if you want to find out this Tm, see here. This is the Tm minus Ts divided by TMI minus Ts is equal to, this is e to the power minus h px upon m dot c. Right. This is the variation of mean temperature. See, this is the Tm now. This is the Tm. Right. This is the Tm minus Ts upon Tm minus Ts is equal to e to the power minus hpx upon m dot cp. What is the h? H is the convective heat transfer coefficient. What is the P? P is the perimeter. No? What is the P? P is the perimeter. P is the perimeter. P is the perimeter. Okay. What is the m dot? This m dot is mass flow rate. This m dot is mass flow rate. And what is this Cp? This Cp is specific heat at constant pressure. Specific heat at constant pressure. Specific heat at constant pressure. Is it clear? And how you are getting this mathematical expression? This is simply from energy balance. Simply from energy balance, right? See here. See, I'm considering a small element at a distance x. So this is the small element. Okay. This thickness is dx. Considering this thickness is dx. Okay. Now, if you apply the energy balance, for this small element, so I say energy balance for a small element, right? And that energy balance is, see here, what is the rate of convection heat transfer, because Ts is greater than Tmi. So from the wall to the fluid, the mode of heat transfer is convection. So what is the convection heat transfer here? I say this simply, this is H into, that is Ta into, that is Ts minus Tm now. I can say this is Ts minus Tm now. At a x distance, the mean temperature is Tm, right? Wall temperature is constant, and wall temperature, that is Ts. dA, what is the dA? The dA is equal to, what is dA? The dA is equal to perimeter into dx na? Okay, and this is equal to, right? Now see, whatever the heat energy transferred via convection, that is utilized to increase the enthalpy rate of the fluid. Is it fine? Now see, whatever the heat transfer that occurs from the wall to the fluid, that increases the enthalpy rate of the fluid now. So we can say this is equal to m dot Cp, and that is dTm. Is it clear? If you're solving this mathematical expression, or if you're solving this energy balance, you are getting this mathematical expression. You are getting, that is Tm minus Ts upon Tmi minus Ts is equal to e to the power minus h p into x divided by m dot Cp. Right. So from here, it is very much clear that mean temperature changes exponentially. Mean temperature changes exponentially with x. Mean temperature changes exponentially with x. Is it fine? Now see, if you want to see the temperature profile, see here. In y direction, temperature. This is the x direction. Fine. That wall temperature is constant. So this is the wall temperature. This is the wall temperature. Right. And how the mean temperature changes? See here. How the mean temperature changes? Mean temperature changes like this. So this is the Tm inlet. This is the Tm exit. At any x, the mean temperature, that is Tm, and this variation is exponential variation. I hope you can understand this. Is it fine? Now see here. There is another very important mathematical expression. See, what is the Q dot? If I ask you what is the total heat transfer, what is the Q dot? So simply you can say na, that Q dot from inlet to exit, from pipe inlet to pipe exit, what is the total rate of heat transfer? So simply I can say this total rate of heat transfer is equal to increase in enthalpy rate of the fluid, and simply I write m dot Cp, and this is Tm exit minus Tm inlet. Is it fine? This is also equal to, this is H into A into LMTD. H into A into LMTD. What is A? So A is simply, this is the surface area or area from where the heat transfer occurs. that is pi into d into L. If pipe length is L, pipe length is L, right, see here, this is the pipe, this is the pipe, the length is L, diameter is D, diameter is D, right. So that is pi into D into L. And what is LMTD? Now this is important, na? What is LMTD? So this LMTD is equal to theta 1 minus theta 2 divided by natural log theta 1 by theta 2. What is theta 1? This is theta 1. 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 What is theta 2? Theta 2. This is theta 2. So what is theta 1? That theta 1 is equal to Ts minus Tmi. What is theta 2? That theta 2 is Ts minus Tme. Okay. So again, this is very, very important mathematical expression, or you can say this is very, very important concept. Number of times the question came from this concept only. Okay. So this is the constant wall temperature case. This is the constant wall temperature case. This is the constant wall temperature case. Okay. Now come to the constant heat flux case. Next case is constant heat flux case. Constant heat flux case. So in case of the constant heat flux case, Q dot is constant, or I say this Q dot is not function of x. This Q dot is not function of x. This Q dot is not a function of x. Q dot is not a function of x. Okay. So I want to see the temperature variation, but first that Q dot, again same thing. I am considering a, see here, this is the pipe, this is the pipe, this is the pipe, and here the mean temperature, this is the Tmi, here the mean temperature, that is the Tme, right. Constant heat flux case is there. So if constant heat flux case, so wall of the pipe is wrapped with the heating coil like this, so that Q dot is constant, not a function of x, not a function of x. Okay. So again, what I am doing here, I am taking a small element at a distance x from the inlet. So this is the dx, and this is a small element. So what is the heat transfer? What is the heat transfer? If you apply the energy balance, for this small element, so simply I can say that Q dot multiplied by dA, this is the total heat transfer, and this is equal to, this is the total heat transfer, and this is equal to, this is H into A into, this is Ts minus Tm. I say na, or H into dA, sorry, H into dA, Ts minus Tm. H into dA, Ts minus Tm, I can say, right. So see, dA cancel out from the energy balance, and this is Q dot is equal to H into Ts minus Tm. We know that in the developed region, if I am talking about the developed region, so in the developed region, this H is constant. In the developed region, that H is constant, so Ts minus Tm is constant, right. Ts minus Tm is constant. Ts minus Tm is constant. Ts minus, or I say, in the developed region, H is constant. H is constant, therefore Ts minus Tm, that is also constant. Ts minus Tm, that is also constant. What is the meaning of that? That means Ts, that in a developed region, that Ts and Tm, the temperature variation of the wall and the temperature variation of the mean temperature, both are parallel. And that both are parallel, na? And if both are parallel, then only you can say na, that at any x the Ts minus Tm is constant. Is it fine? Is it clear? Now see here, parallel. Now see, next. This Q dot into dA, this Q dot into dA, this is also equal to, this is a m dot Cp dTm, na, you can say. And this dA is perimeter into dx, na. So this is Q dot into P into dx is equal to m dot Cp, and that is dTm. So ultimately that is dTm by dx is equal to, this is dTm by dx is equal to Q dot P upon m dot Cp. Now see here, Q dot is constant, flux is constant, perimeter is constant, mass flow rate is constant, Cp is constant. So ultimately this dTm by dx term is constant, and dTm by dx is nothing but the slope of the mean temperature, or slope of the mean temperature variation, right? Slope of the mean temperature profile, na? This dTm by dTm by dx. If dTm by dx is constant, if slope is constant, that means that is a straight line. That is a straight line. Is it fine? So here see, if you see the temperature variation, if you see the mean temperature variation, if you see the mean temperature variation, so that mean temperature, this is the mean temperature variation. This is the mean temperature variation. Is it fine? This is temperature, and this is x, right? And in the developed region, right? This in the developed region, if you want to see the wall temperature variation, so wall temperature variation, this is the wall temperature variation. This is the wall temperature variation. This is the wall temperature variation. Right? This is the wall temperature variation. So in the developed region, this is the developed region. 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 Developed. This is the developing region. This is the developing region. And in the developed region, at any x, developed region, right here, this temperature difference between the Ts and the Tm is constant at any x in the which region? In the developed region. So this shows the Ts of x, matlab temperature variation of x, and this shows Tm of x. That means temperature variation, mean temperature variation with x, right? A straight line. Now, what happened in the developing region? 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 In developing region. In developing region. So in developing region, that H is not constant. H in the developing region, this H decreases, na? This H decreases. So if H decreases, so Ts minus Tm increases, na? Why? Why this increases? Because that Q dot is equal to H Ts minus Tm. This is the constant heat flux case, so this should be constant. But in the developing region, this is not constant. This is not constant. This decreases. That's why this term should be increases. This term should be increases. Right. So in the developing region, this Ts minus Tm increases. Now see here. Ts minus Tm increases. Now see. In the developing region, see. Okay. This is the temperature profile. This is the temperature profile. So in a developing region, see here, in a developing region, right, this temperature difference, mean temperature difference and the wall temperature difference increases, right? And in developed region it is constant. In developed region it is constant. Is it fine? And if you want to see the energy balance, so this Q dot multiplied by pi into D into L, this is equal to m dot Cp Tme minus Tmi, right? What is the total rate of heat transfer? Constant heat flux case is na. In case of the constant heat flux case, what is the total rate of heat transfer? The total rate of heat transfer is Q dot into pi dl. Q dot into pi dl, and this is equal to, this total rate of heat transfer is equal to increase in the enthalpy rate. Na? This is equal to increase in the enthalpy rate of the fluid. Whatever the heat transfer is there, that is utilized to increase the enthalpy rate of the fluid, right? So I can say this energy balance. Okay, in case of the constant heat flux case. Okay, so this is all about the internal forced convection. This is all about the internal forced convection. Is it clear? So I hope you can understand each and every concept related to the internal forced convection. Okay, so thank you so much for this session. Okay, so bye bye, take care and have a good day.